Thank you very much. It is great pleasure for me to speak again and again, but what is now it is becoming very boring because we have more seminars and the work, but it is a lot. Okay, so I'm very sorry for taking your time, but today I will speak about the cosmological problems and what is interesting happening is there. So in introduction I will say then the main concentration on the large-scale structure of the universe, and then cosmic inflation, and then I will. So if you compare astronomy and astrophysics to other natural sciences, all natural sciences are based in experiment, even mathematics. In mathematics you have numerical experiments, but astronomy and astrophysics is totally different because it is based on observations. And then what is important for observer that the signal from the far object, astrophysical object, should reach you without any deflection in the pure form. But what happens in the reality, our atmosphere is very terrible. So this gamma ray and X-ray, these high energy photons are totally blocked. Then there is visible diapason, wavelengths, so it is also disturbed by atmosphere, and then we have only in the meter diapason radio waves which penetrates the atmosphere, not disturbed. Okay? Then it is a big problem, because we have a big problem of observation of the far objects due to the atmosphere, which disturbs the signal which comes from the infinity, almost, yes. And then what happened in the last century? In 1957, I say that it is the main discovery by mankind happened in 1957, when for the first time the satellite, artificial satellite, left the gravitational field of the Earth. Then it created huge area of development of astronomy and astrophysics, because now we have armada of the telescopes which observe in the whole electromagnetic wavelengths, and if initially in the beginning of 20th century the ratio of the wavelengths was equal to 2, so it was between 4,000 and 7,000 angstroms, but now this ratio is 10 in power 16. So, and the cosmic telescopes created very high resolutions of the astronomical observations, which led to the revolutionary discoveries, for example, in cosmology. So we did not know that the universe, for 96% of the content of universe, was unknown. So we did not have any idea about 96% of the universe. Now we know that there is some part which was not, which was unknown for us. Then it is dark energy and dark matter, and everything is consists only 4% of the universe. And here you can see this is most famous telescope for many decades, so Hubble telescope. This is 2.2 meters, and this is becoming very important now, James Webb telescope, which is operating Spitzer, the integral. So here what was important, so now we have armada of the X-ray telescopes which can observe the, for example, for the black holes in the electromagnetic spectrum. So this is all are the telescopes which are orbiting the Earth. And what happened in astronomy from point of view of the cosmology, I say here you can see the first cosmological model was suggested by Claudius Ptolemy in the 2nd century. So it was a geocentric model, and it was totally based on the observations. Because why it was based on the observations? Because it was seen from the Earth that the far stars do not move; they are static. So it was indication that Earth does not move with respect to the stars. But it is similar when you take this Opavian train to Prague. So you can see that trees are moving with respect to you, so it means that your train is moving. But here, Claudius Ptolemy did not see any motion of the stars, and then he assumed that the stars are constant. They're not moving, they're static. And here in the model, he did not imagine that these stars are very, 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 very far. So it was then this in 16th century Ptolemy has shown that our model is sun-centered, so it is heliocentric, and then in 20th century it is the Big Bang cosmology came, so it says that it created about 14 billion years ago, and now the density of the matter, it is expanding 10 in minus 29 gram per cubic centimeter. So Einstein, he was the first who has got the cosmological solutions of the Einstein equations. Friedman, who did not agree with it, and he has shown that the curvature of the space-time should change with the time. Our universe should either expand or either squeeze. So curvature should depend on the time, so it was mathematical model, and Edwin Hubble has shown that the galaxies are moving away from us, and then now we say that universe is full of the galaxies. We have 100 billion of the galaxies, and each galaxy has 200 billion stars, and it is always becoming bigger and bigger, and the distances which we use in the solar system do not work for the universe. So for the universe, we usually use parsec or light years, and in the solar system we have sun and orbiting planets, which each planet moves with respect to the sun according to the Keplerian law. So, and the sun is moving with respect to the central object, which we now becoming very famous object, which is called Sagittarius A star, and it is about 28,000 light years away from the Sagittarius A star, and it makes one revolution in 230 million years. So this we know. And then, since we have so many stars, there is the question, are there other exoplanets orbiting other suns? And the answer is yes. So there was Kepler mission for the finding easier to observe bigger planets. Now we have we know that this planetary system is very common in our galaxy. This year NASA announced about 5,000 confirmed exoplanets observed. And what is interesting here, and even there is potentially habitable exoplanets, even very close planets show that the life can exist there. So it is very promising, and it is very good. And what is the dark matter? So we said that 23% of the universe consists of the dark matter. What is it? So first time about the dark matter in 1933, Estonian physics epic and American physicist Fritz Zwicky said that they were looking to the common galaxy cluster, motion of the galaxies, and then they observed that these galaxies move with very high speed, and but the virial theorem was showing that speed should be much less, and then they assumed that there should be some matter which we don't see, but it is they suggested that there is some unseen matter, what is now called as dark matter. But first confirmed, strictly confirmed data was obtained by Vera Rubin in 1975, when she observed the rotation curves of the galaxies, and she has shown that the stars move with almost constant velocity when they go further from the center of the galaxy. And all other, there are too many observations, for example, cosmic microwave background fluctuations also say about existence of the dark matter, so there are about, this is very Rubin, and the task is very simple. So, for example, we know that the planets are orbiting Sun on the Keplerian orbits, and then if I will make, according to this formula, this theoretical line, all planets in the solar system, they match exactly to the theoretical line. So what it shows, that there is no effect of dark matter in the solar system. Solar system is totally governed by the gravitational force of the Sun. Sun is the main dictator of the solar system. Nothing can change the motion of the planets except the Sun. This we know exactly from the observations. But what happens with the stars in the galaxies? The stars in the galaxies, for example, this red line is the theoretical curve. So it shows that in the far distance from the center of the galaxies, velocity of the stars should go down, but measurements show the totally different observation. So they show that there is something which makes stars moving faster and faster. So it is very similar to the model of Thomson of the atom. So there is something, some matter, which is which interacts gravitationally and makes stars moving faster than they should be moving. So their speed exceeds 200 kilometers per second, even very far distance. So, and now what we can do, we can weight the matter in the galaxies through gravitational lensing. This is the dark matter. So here you can see the distribution of the dark matter, which does not coincide with the distribution of the gas, of the hot gas. So it means that there is no interaction between dark matter and the hot gas, which is in this cluster, and this can be seen here very clearly. So this white one, these are galaxies. White one is the distribution of the matter. So matter, since it interacts, so it always tries to find the place where there is gravitational minimum. So they go to the minimum. It is very similar to what happens with the water during the rainfall. Yes. So if there is some hole, water will go there because water is interacting. But here, what we can see, this is distribution of the dark matter. Dark matter does not interact. It does not care of it. So it means that the interaction of the dark matter is extremely big. So, and then there is, we may think about the candidate of the dark matter, and first assumption comes, probably it is gas. It may be ionized or neutral or so, but the amount of gas is not enough, and then we may think about matter. Matter is the massive compact hollow objects, so it is usually black holes or other objects, but observations show that their number is very low, so it is not enough to explain the dark matter. So these two candidates do not work. And most probably it is the dark matter, it is weakly interacting massive particles. People say it is WIMP. So what is the WIMP? For example, we have huge number of neutrino in the universe. For example, 320 neutrinos per cubic centimeter, but the mass of neutrino is not enough to explain this mass. Okay? So we need to find some elementary particle which is very similar on behavior of interaction as neutrino, but it is heavy. So then, if this particle would be found, then we can say that at the moment it is not experimentally detected. So at the moment we don't know what is the from what dark matter is made, and now we call it as dark matter. So there are candidates. And what is the dark energy then? So for example, we don't know what is it 96% of the universe. Then we divide it into two substitutes. So one of them is dark matter, and one other one is dark energy. So what is the difference with dark matter? Dark energy is distributed homogeneously. So you saw that when we look to in the galaxies, in some places there is dark matter, in some places there is no dark matter. But for dark energy, it is distributed everywhere homogeneously, and it does not depend on the time. So it is always the same. So it is, and and on other hand, it has anti-gravity. So if dark matter is attractive, dark energy is repulsive. And the equation of this of state, it is P is equal to minus rho. So dark energy creates anti-gravity. It is the reason why at the very far distance the galaxies are moving with acceleration. Okay? So this we know from the observations, and for the first time the accelerated expansion of the universe was detected from supernova 1A. So it is supernova 1A, which is more bright than the universe, and how supernova 1A creates. So it is in the binary system when we have white dwarf accreting matter from in the low mass X-ray binaries. So this white dwarfs takes energy mass equal to 1.4 solar masses, Chandrasekhar limit. Then it explodes, and then we know what the energy is released. And knowing the energy, we can, for example, look to the integral intensity of this 1A during 1 year, let us say, and then compare, get r squared the distance to the object. But when people started to this standard candle to look to the very far galaxies where supernova 1A exploded, so it was found that these objects do not fall to the Hubble law. So they went somewhere, they were darker than we assumed, so they were more far than we assumed. So it was the first indication about the existence of the dark energy, and these three guys, Perlmutter, Schmidt, and Rice, have got Nobel Prize for the discovery of the dark energy. And what is interesting here, according to the modern standard cosmological model, so you see, we can construct from this, we said, we have three constants, Hubble constant, speed of the light, and Newtonian constant. From the Newtonian constant, I can construct Planck time. So it is 10 in power minus 43 seconds. So now what cosmologists say, our universe is created through from inflaton, and up to 10 in power minus 43 seconds, the time and let us say space was the same. So it was not possible to extract. So now, for example, I can take a roller and measure the distance, and then my clocks measure the distance in the time interval, yes? But at the up to 10 minus 43, there was no such option. So, and then up to 10 in minus 35, there was inflation, and then there were created the particles, but the first 3 seconds, all matter was created, hydrogen and helium, which exist in the universe. But this matter was in the plasma condition. So there were electrons, and the temperature of the universe was decaying in the, for example, if you take 10 in power 10 Kelvin divided to T over square root in seconds. So then, if you put to this formula the time in the seconds, you can get that when the universe was 380,000 years old, the temperature of the universe dropped to 3,000 Kelvin. When it was 3,000 Kelvin, the neutral atom started to be created. So before this 3,080,000 years, all photons were scattering in the electrons, and they were not able to move for the distance, and the universe was lighted. But from this, they interacted all last time, and then the dark age background, so which is observed. So from that period, so it is decreased for 1,100 times, and now it is 2.7 Kelvin. So it is the temperature of the relict microwave background. Here you can see it is the image. So when you look to the image of the universe, so it is the image of the universe when it was only 380,000 years old. So it is very baby universe. And then here you can see the spots. So these red spots are when the temperature is higher for microkelvin, but blue spots when temperature is lower for microkelvin. Then in this resolution we see that there are some structures in the initially it was homogeneous with low resolution, and now what is interesting here, when we decompose it, the number of the spots which have size about 1 degree angular size is majority. So we have a big number of the hot spots about 1 degrees, and what it says. So when we simulate, so simulation of the microwave background shows that if we will have the initial fluctuation delta rho divided to rho less than 10 minus 5 or bigger than 10 minus 5, nothing happens in the universe. So this is exact number, and the same with the temperature. And here what you can get. So if you will get the simulation for the flat universe will show that the spot should be about 1 degree. The observation shows the same. So the simulations and observations show that our universe is flat. So it should be, it should have or negative or positive curvature, but it is flat. So why it is flat? It is very similar. We are in the globe, but sitting in the home, I look to the floor and I say that the floor is flat. So it is very small size with respect to the Earth, and then for us it is flat. The table is also flat. So I don't see that I'm living in the globe, sitting in the home. It is similar with our universe. We are sitting in some very small area. The universe is very huge, and it looks like flat for us. So it is what we see, and here you can see the, for example, initially this is the dark energy. Yes, you see, dark energy does not depend on the time, so it is always constant. So initially, up to 380,000 years old, the radiation was dominating. So here there was radiation dominated. Then from this point up to this point, it was matter dominated. But now we are living in the era of the dark energy dominated era. So the main constituent of the universe is dark energy. Okay. Now what we say that we said that our universe consists of the galaxies. So these galaxies also make some groups. For example, in our group we have local group of the galaxies, and then these local groups of the galaxies are part of the other clusters. So here you can see how it looks. Our solar system, Sun is orbiting the Earth is orbiting. So we have 10 in minus 18 meters. So it is you see what is the scale. So we can see the ratio between them in 10 in power 45 between biggest and smallest object in the universe which we observe. So this is what we can see. And if we look to the time, in the time it is even bigger. So it is 10 in power 14 seconds divided. So it is 10 in power 63 seconds. So we have resonances in the strong field regimes. So these resonances are maybe 10 in less than 10 in power minus 21, minus 23 seconds. And then we have the most stable object in the universe is proton. So we say that the period of the decay, half period of the decay of proton is 10 in power 40 seconds. So this, and then all matter consists from quarks, so with this nose, and there are some interactions. So in the long range, we have only two interactions, electromagnetic and gravitational. So these are two interactions which can go to the long range. But when you look to the ratio, so the ratio, so if it is the electromagnetic with respect to the strong interaction, it is 10 minus 2. But when we compare with the strong interaction, the gravitational is 10 minus 38. So it is 10 in power 36 times weaker as compared to the electromagnetic force. And then you may ask the question, why in the astronomical distance gravity dominates? What is the reason for this? Why it is being very weak, it dominates? But it is due to the fact that the electromagnetic radiation interaction has positive and negative charge. So whenever you collect many particles, the net charge will be 0 because you will have positive and negative charge, and the net charge is 0. But in gravity, so whenever you put more and more particles, your mass will grow, and for the astronomical objects are very huge. As I said, mass is very important, and then in the universe, gravity dominates. So the main force in the universe is gravity because it has only one charge. It is the reason. And why now we are comparatively happy, but then the problem, why this inflation model necessary? Why we need to go to the inflation model if this Friedman model is, everything looks all right? But the problem is the following, because the question was given even to Einstein, what was before the Big Bang, when there was nothing, so we don't know. So, but Einstein said there was no time, so I don't want to say about non-existing thing, but it is a philosophical answer, but we need to understand what is it. And then, why the universe is uniform and homogeneous. So if I will take universe, it is at the, let us say, 100 megaparsec scale, it is uniform and homogeneous, and why all parts of the universe have started to expand simultaneously, why the universe is flat, so it should be curved, and this why the universe contains so big number of particles, and this problem was first time solved by Alan Wood in 1981. But it is not model, it is hypothesis, because it explains. But I should say everything which is model should be confirmed experimentally. But for the inflation model, we don't have enough experiment. So the I think in 2015 there was BICEP. So it was looking to the polarization of the modes of the cosmic microwave background, and there was announcement this it was observed, but somehow it was due to the dust, so it did not work now, but it will work. And then it was developed by Starobinsky, Linda, Mukhanov, and many other theoreticians. So what is the idea? So they say that, for example, can we create particles from nothing? These people say yes. They say, for example, if you have gamma quant, so gamma quanta, two gamma quanta will decay to the positron and electrons. So from gamma quanta, you can create through quantum processes, you can create the elementary particles. So they say that there is physical vacuum. So physical vacuum is different from the technical vacuum. So when we say about vacuum, we say that it is the air where it is, you make it rare and rare with pump, yes? And then you can create some technical vacuum which will anyway have some particles, but here it is physical vacuum. In the physical vacuum, you will have some fluctuations, and then this fluctuation will create you some particles, and usually these small quantum fluctuations, the particle which appear will come back, and suddenly some large quantum fluctuation can come and create some scalar field with this potential. So this is large quantum fluctuation can create our universe. Okay? Then this here you have very large phi, and h is very high, and it is this field is governed by Klein-Gordon equation, which is very similar to the equation of the harmonic oscillator with the friction. Yes, and here, if h is very big, you see, h is big, constant, so you get a over r is equal to constant, and then you can integrate. Yes, and then what you can get? So this solution of this equation, if h is big and constant, then you can get exponential for A. So it is the scale factor of the universe, which is at the initial stage. So our universe is started from inflation, so it expanded very rapidly. So it is the inflation stage, and inflation stage, so the universe is increased in 10 in power 10 in 12 times, in the time scale between 10 minus 43 to 10 minus 32 seconds. And what happened here, so it is very, it is curved, let us say, but we see only a small part of it, because there was a change of the signal at that time, and we see other part is not seen for us. So we see only observational universe, which look exactly as flat, because we see some part, but I will not discuss this in deep detail. So now what we know from the universe, yes? From the universe, from the first, from the inflation model, so our universe was created from nothing, from physical vacuum. There was inflaton, which expanded and created our universe. And then, during the 3 minutes, the first light nuclei were created. So, according to this gamma model, so let us say 8% of initial, so it was 92% of matter was from hydrogen and 8% from helium. So there was nothing. But now, when we look to the environment, we see many heavy elements. Where they're created, and for this, most important thing, so the elements up to ferrum, up to iron, are created through nuclear fusions in the stars, in the main sequence stars, but then we have uranium, gold, platinum, and many heavy elements. Where they were created, and the explanation for this is the fullerene. So it is due to the gravitational waves. If there would be no gravitational waves, the mankind would not appear, because we need to have heavy elements in the body, but these heavy elements would not exist in the universe. Because you see what happens in the binary systems, so we say that many stars are part or are components of the binary systems, but binary systems try to reach each other. Why they come close to each other? Because they radiate gravitationally. Due to the gravitational radiation, they come closer and closer, and then they merge each other. But when they merge each other, so we have 10 in power 57 neutrons, which collide with 10 in power 57 neutrons. So we have huge number of neutrons which bombard the elements which exist in the space, and it is called R process, rapid process, and during very short time the very heavy elements are created. So it is called macronova explosion. So this was observed through gravitational waves. Now we know that gravitational waves are the source of the heavy elements which exist in the universe, and this was Nobel Prize for the discovery of the gravitational waves. And here we can see different regimes. What is interesting, as I said last time, so this is the 0.43 seconds. This is the black hole relative velocity. Can you imagine in the universe the object which has 30 solar masses moving with the speed which is equal to 0.5 c, and then it merges with the other black hole which moves with the same velocity. So it is huge catastrophe. Yes. So then it is what mankind even so cannot imagine it. So if you look to the in the peak gravitational wave luminosity, you see it is 3.6 times 10 in power 56 erg per second. So it is very huge luminosity, so which exceeds the luminosity of the whole universe. So it is from this point of view, it is very. So let me to come to this part. So I say in the 21st century. So if you look to the astronomical objects, so what object is studied deeply? I say sun. Sun is, so we have helioseismology. Sun is studied very deeply during the last century, let us say, yes? But this object, gravitational wave 1708-17, so was observed in 2017, and it created the new era in astronomy. Now we have multi-messenger era. So why it is multi-messenger? Because it was the first time when we observed the same object through gravitational waves and through whole electromagnetic spectrum. And what was happened? So signal, so gravitational wave signal came up to after 2 seconds we had this gamma radiation, and after 10 hours we observed in the optics, and then infrared, ultraviolet, and then X-ray, and then in the radio diapason after 16 days. So we observed this object in the whole electromagnetic spectrum. Here you can see how it was observed, but since it was in the southern hemisphere, so first time it was observed by I think Chile, yes, then it went to the South Africa and Australia. So these 3 telescopes were observing it, and what is interesting here, this SWOP telescope. This telescope is very small telescope, so it is 45 centimeters telescope. Have observed the great event. So when here you can see the signal after 10 hours, and this is, you can see after, let us say, 16 days, there is nothing. Yes, so this signal was dropping, and it coincides with the theoretical models. So theoretical models say that there was gamma ray burst, which was observed, and plus the macronova explosion shows this how it was observed. Why it was observed? Because you see, we have now more than 100 gravitational wave events in the universe, but only for this we know the location. All others are unknown because we say that black hole collision, electromagnetic counterparts for them is very difficult to observe because they don't have nothing, so they don't have hair. So it confirms no hair theorem. So, for example, you see this integral and Fermi were giving huge area in the space where it can be observed, and LIGO, Virgo together gave the area where this event was happened. But when people look to the space, they have found there were 49 galaxies. So this event happened even for the small in the distance range. It was 49 galaxies, but then swap is observed is in the edge of one elliptical galaxy. They observed this event, and the location of this event was found, which was very important. Here it is, and here you can see the brightness. So in the millions of the sun luminosity. So when we look to the, initially it went to the 200 million sun luminosity. So it was very bright, so it is blue, so it is related with the temperature, and it was decaying. So it is 1 day, 2 days, and on the third day it became red, and here you can see that in the several days it was decaying, so it is totally consistent with the macronova explosion model. So now we exactly know that the heavy elements are produced during the neutron star collisions. So this is a strong confirmation. Here you can see the distribution of the elements in the universe. So hydrogen, it is the main constituent of the universe is hydrogen, and we can see it even from the men. What do you think? What is the percentage of hydrogen in my body or in your body? Jirka?
85?
I think it should be big. Yes, maybe 80. Yes. So nature cannot do something, man from something which do not exist in the universe, which is more exotic. So it makes it from the most spreaded element. So most spreaded element is hydrogen. So majority of the atoms inside me are hydrogen. Yes. So this I see definitely. And then there is helium. So we said that 8% of the. So these are elements which are produced after the inflation. So in the Big Bang fusion, yes, because the temperature was enough to produce these particles, but then it was temperature was dropping, and then temperature was not enough to produce other elements. Then it stopped producing. And here you can see these violets are totally produced during the merging neutron stars. So you can see platinum or gold or uranium totally. So you have nuclear power stations here, and it uses uranium as fuel, and it is totally produced during the collisions of the neutron star with the neutron star. This we know exactly from the observation of this event, so this can give you many other things. And now, what is the future for the gravitational wave astronomy? So, what is interesting for cosmology? For cosmology, we say that we have standard model. You see what used to visit with Professor Zdeněk Stuchlik at Trieste in the 90s, and there was the head of the group was Denis Sham. And what he was telling, so in 1965 was holiday for cosmologists. Why? Because during the 50 years, the whole cosmology was based on one fact, so on one experiment, which is the Hubble expansion, so this gravitational redshift, which was observed by the Hubble. But in 1 year, this cosmic microwave background by Penzias and Wilson came, and the experimental base of the cosmology is increased to factor 2. So in addition to one experiment, we started to have 2 experiments. But now we have plenty of data. So we have huge data. So what is changed in the, I think, during the last 5-6 years, the relativistic astrophysics and cosmology changed very rapidly. So now it became observational and experimental area. So now we have a big area. And what is interesting here, since this cosmic microwave background was observed, in this Planck mission, WMAP and others, they were looking to the fluctuation of the temperature fluctuation of the cosmic microwave background. But now there is huge interest looking to the polarization. So what is the polarization? So if we will make a good resolution for polarization, we can get information about the relict gravitational waves. So then CMB polarization will give us relict information about relict gravitational waves. They would be detected, and then looking to the relict gravitational waves, we can confirm the inflaton. And so confirmation of inflation model should come through observation of the polarization of the cosmic microwave background. And when we look to the recent observation, so these terrestrial interferometers, LIGO, Virgo, they work at the up to, let us say, 100, 300 or 400, 500 hertz. So it is the diapason wavelengths where it will work. But then it will go to the LISA or other objects, so this space-based interferometer up to this frequency. So this is for the future. So this can give us information about compact binary in spiral and merger. It is terrestrial and space-based observatories, and other thing is related to the radio pulsar timing arrays. So this will give us about the merger of the supermassive black holes, and the universe will be studied through polarization of the cosmic microwave background. This is what we see for the future in the astronomy, and I wanted to finish it with the young scientists who do real research in our group. So these are, for example, Arman Tursunov and Bobomurat Ahmedov. So in our country there is a 2-step degree. So these people who have got degrees, so this is Arman in 2019 and Bobomurat Ahmedov recently. So these 2 guys we are very thankful to Silesian University for creating such good scientists. And Ahmadjan, you know him. And these guys were trained at Fudan University in Shanghai, and Jalon is going to defend Doctor of Science. This is Shurad Mardon from the Spain, and we have one guy, Sanjar Shaimatov, from the previous, who is also going to defend Doctor of Science. And here you can see the theoreticians who made very big contribution to the cosmology, to the development of the cosmology. This Friedman, who first made the dynamical model of the universe, Lemaitre and Albert Einstein, because you know that this there is some big debate, for example, International Astronomical Union in Vienna, there was big discussion who discovered the Hubble expansion. So Lemaitre wrote notes in the French where he has observed the redshift of the galaxies. So there was claim from the International Astronomical Union to rename it as Lemaitre-Hubble law. So it is. So you know that Hubble made big contribution, and this is Georgy Gamow, who. So you see when this came expansion. So cosmologists were divided in two groups. One part of cosmologists were saying that the temperature at the beginning stage of the universe was hot, so it was very high. It is the Gamow direction, and then there were people who were telling that the initial universe was cold universe, and I think in Soviet Union the cold universe was more popular as compared to the because it was suggested by Gamow, and it was the reason that Zildovich was at the side of the cold universe. But in spite of this, when this Penzias and Wilson observed in 1965, they went to hot very fast. So they made very big discoveries in very fast time because they were very, very clever people. So, and then this Hermann and Alper, who were working with Gamow, because Gamow was he was very happy from his surname. So, and he was working with Alper, and when he wrote a paper, he approached Hans Bethe to be co-author. So because he wanted to create a cosmological model alpha, beta, gamma. So the authors were Alper, Hans Bethe, and Georgy Gamow. So it is the alpha, beta, gamma. So these theoreticians made big contribution, and this guy is Rashid Aliyevich Sunyaev, and actually he's from Tashkent, and Jim Peebles, who has recently got. So usually nobody from theoreticians have got Nobel Prize for cosmology. Even Einstein has got for something else, but he is the first theoretician who has got Nobel Prize for theoretical cosmology. So now we hope that we will have more Nobel Prize laureates for theoretical cosmology. So up to now it was only for observations, and then thank you for your attention. So it is what I wanted to discuss today about cosmology, and from my point of view, now cosmology is becoming very hot topic.